The universe begins in silence, not the silence of absence, but the silence before music. A black ocean of potential, dense beyond imagination, holding all that would ever exist. Then, a moment beyond moments, the first light. Not a beam as we know it, but a flood of pure energy, an ancient illumination born from chaos itself. This light would pour through the newborn cosmos, a messenger from the very edge of time, seeding the structure of galaxies, stars, and worlds yet unformed. It would carry the fingerprints of creation, whispering in its faint glow the story of everything. And even now, more than 13 billion years later, it is still here, stretched thin by the expansion of space, a ghost of its former brilliance, yet still shaping our understanding of reality. This is not just light, it is the oldest photograph of the universe, a memory etched in radiation, guiding humanity toward answers to the deepest question of all. How did it all begin? In the early 1960s, the universe seemed vast but strangely incomplete. Astronomers could see the scattered light of countless galaxies, could measure the spectra of stars, could even chart the great spirals and clusters scattered across the night, but there was no direct proof of how it all began. Two competing visions of the cosmos dominated. One, that the universe had always existed in a steady state, eternally forming new matter as it expanded. The other, that it had emerged from a singular moment of creation, hot, dense, and unimaginably small. Both were grand. Both were uncertain. It was into this quiet tension that two radio astronomers stepped, not in search of the universe's birth, but simply to remove an unexplained noise from their data. At Bell Telephone Laboratories in Homedale, New Jersey, Arno Penzias and Robert Wilson were tasked with refining a sensitive microwave antenna, a massive horn-shaped instrument designed for satellite communications. Its shape was engineered to capture the faintest whispers of radio waves without the distortions of a traditional dish. But there was a problem. No matter where they pointed the antenna, at the horizon, toward the galactic center, into the vast emptiness above, a faint, persistent hiss filled their receivers. It was a uniform glow, constant through day and night, summer and winter. It was not the chatter of nearby cities, nor the signature of known stars. They suspected faulty equipment. They checked every amplifier, every connection. They suspected the air itself, so they measured through seasons. They even suspected life, or at least its remnants, for inside the antenna, a small population of pigeons had made their home. The astronomers cleaned out the nests, removed the droppings, ensured the horn was pristine. Yet the hiss remained. What Penzias and Wilson did not yet know was that, only 60 kilometers away at Princeton University, Robert Dick, Jim Peebles, and their colleagues were preparing an experiment of their own. They were searching for something predicted by cosmology's hot Big Bang model, a background glow of radiation, cooled by billions of years of cosmic expansion, now invisible to the eye but still detectable as microwaves. The Princeton team had the theory but no signal. The Bell Labs team had the signal but no theory. When word reached Dick of the strange noise measured in Homedale, he reportedly turned to his colleagues and said, "Well boys, we've been scooped." In that moment, the two paths, accident and prediction, converge. The hiss in the Bell Labs horn was not interference. It was the afterglow of creation itself, the cosmic microwave background. A sea of ancient light, stretched to the wavelength of cold microwaves by the expansion of space, bathing the universe in a near-uniform glow. This radiation had been traveling for 13.8 billion years, carrying in its faint variations the blueprint for every galaxy, star, and planet that would ever exist. The discovery was more than the detection of a signal. It was the first direct glimpse of the infant universe, a photograph not of stars, but of time itself. The news rippled quietly at first, a conversation between colleagues, a murmur passing through physics departments. But those who understood what had been found, truly understood, realized they were witnessing the collapse of an old vision of the universe. The detection of the cosmic microwave background was not just another point on an astronomer's chart. It was an artifact from a time before galaxies, before stars, before even atoms as we know them. The radiation Penzias and Wilson had uncovered was born when the universe was only 380,000 years old, an infant cosmos compared to its present 13.8 billion years. This light, now stretched into microwaves, was the faded ember of a furnace so hot and dense that matter and light were once inseparable. For decades, cosmologists had debated two irreconcilable pictures of reality's past. The steady-state model claimed the cosmos had no beginning, that it was eternal and unchanging on the largest scales. It was a comforting vision, elegant in its simplicity, no singularity, no creation, no before. Opposing it was the Big Bang model, the radical idea that all space, time, matter, and energy had burst forth from an initial singular point, expanding and cooling ever since. Both camps had gathered evidence, but none decisive enough to silence the other. The CMB changed that overnight. Here, at last, was the unmistakable fingerprint the Big Bang theory had predicted. A steady-state universe could not produce a relic radiation field of such uniform temperature and distribution. This was fossil light, a remnant of a primeval fireball, preserved across all directions of the sky. And yet, as with all great discoveries, this revelation came with its own disquieting strangeness. First, its perfection was unsettling. The radiation's temperature was astonishingly uniform, about 2.725 Kelvin above absolute zero, varying only by tiny fractions of a degree. Theoretically, this suggested that distant regions of the early universe had been in contact, sharing heat, but the known laws of physics implied they were too far apart, expanding too fast, to ever have exchanged information or energy. This contradiction would later be called the horizon problem, a riddle hinting at a deeper mechanism in the first instance of cosmic history. Second, the CMB's very existence raised profound questions about the nature of time. If this light had been traveling for nearly 14 billion years without losing its coherence, what did that imply about the geometry and curvature of space? Was the universe infinite, wrapping back on itself, or open, expanding without bound? The CMB did not answer, it merely framed the question in sharper relief. Then there was its silence. Beyond the faint temperature ripples, the CMB carried no obvious imprint of life, structure, or purpose, just an impersonal glow, indifferent to the galaxies and civilizations that would later arise. It was a reminder that the universe's earliest chapters were written without us, in a language of radiation, plasma, and gravity. For the community of cosmologists, this was exhilarating and disorienting. The CMB had confirmed the violent origin of the universe, and in the same breath, it had revealed gaps in the most trusted theories. As Stephen Hawking would later remark, every new piece of knowledge in cosmology is also a new horizon of ignorance. Within months, observatories around the world began retooling their instruments to measure this relic radiation more precisely. Radio dishes turned skyward not for stars or galaxies, but for the dim glow between them. What emerged was an image of the universe in its infancy, smooth, featureless, and yet hiding in its subtle irregularities the seeds of everything that would come. The shock was not just scientific, it was philosophical. If the CMB was the light of creation, it implied there was a moment when time began, a moment when there was no before. It forced humanity to confront a possibility that ancient philosophers had debated and poets had imagined, but science had never before proven, that the universe had a birth. And with that birth came a cascade of uncomfortable questions. What, if anything, preceded it? Did the laws of physics themselves emerge from that first moment, or did they already exist in some pre-cosmic state? And if they emerged, could they one day change again? The CMB was not a quiet discovery. It was a cosmic alarm bell, one that shattered an old order of thinking and opened the way to an entirely new map of reality. And for those who listened closely, it carried another, more haunting message, that the more we learn about the universe's origins, the more impossible it becomes to ignore the infinite unknowns that still lie beyond. The CMB's discovery had been an accident. What came next was anything but. From the moment its significance was understood, a new race began, not to find the radiation, but to listen to it with ever greater precision. If this truly was the universe's first light, then hidden within its faint glow must be a record of the cosmos's earliest moments, a kind of cosmic diary, waiting to be read. The first instruments were crude by modern standards, ground-based radio telescopes shielded from city noise, listening to the sky in the microwave band. They confirmed the CMB's remarkable uniformity, but technology limited the details they could resolve. For the great questions that now loomed, how galaxies formed, why the universe had the structure it does, scientists needed something far more sensitive. In the 1980s, the United States launched a bold mission, the Cosmic Background Explorer, COBE. Its purpose was audacious: to measure the CMB's spectrum and map its minute temperature variations across the sky. In 1992, COBE's data electrified the scientific world. The satellite confirmed that the CMB's spectrum was an almost perfect blackbody curve, matching exactly what the Big Bang model predicted. And then came the image, a map of the sky showing the tiniest ripples, mere tens of millionths of a degree, spread across the uniform globe. Stephen Hawking called it the discovery of the century, if not of all time. These ripples were the seeds of cosmic structure. Quantum fluctuations from the earliest fractions of a second, stretched to cosmic scales by the universe's expansion. Over billions of years, they would collapse under gravity to form stars, galaxies, clusters, and, eventually, life. The revelation was profound. We were staring at the blueprint of the cosmos, imprinted in light older than the oldest stars. Yet the patterns also whispered of deeper mysteries. The scale and amplitude of the fluctuations were exactly as certain theoretical models predicted, but to match the observed smoothness of the CMB, the early universe must have undergone a sudden, staggering expansion, cosmic inflation. Proposed in the early 1980s, inflation suggested that in the tiniest fraction of a second after the Big Bang, the universe ballooned faster than the speed of light, ironing out irregularities, and setting the stage for everything that followed. The horizon problem, that puzzling uniformity, now had a possible answer. But science is rarely content with possible. To test inflation, greater detail was needed. This led to the launch of the Wilkinson Microwave Anisotropy Probe, WMAP, in 2001, and later, the European Space Agency's Planck satellite in 2009. These missions delivered CMB maps of unprecedented precision, revealing not just the temperature ripples, but their polarization, a faint signature of how light scattered in the early plasma. The data spoke clearly. The universe is about 13.8 billion years old, composed of roughly 5% normal matter, 27% dark matter, and 68% dark energy. Yet these precise numbers did not bring closure. They deepened the mystery. Dark matter and dark energy were not just unknown, they were utterly invisible, detectable only through their gravitational fingerprints. The CMB had done more than confirm the Big Bang. It had unveiled a universe far stranger than anyone had imagined. At first, the CMB seemed to be a triumph of order, a smooth, elegant remnant from a well-understood beginning. But the closer scientists looked, the more unsettling details emerged. One of the earliest surprises was the so-called axis of evil, a strange alignment of the largest-scale temperature fluctuations. Instead of being entirely random, as theory predicted, some of the CMB's largest features seemed to line up along a preferred axis across the sky. Was it an artifact of measurement? Or could the universe itself have an orientation, a cosmic asymmetry woven into its birth? Then came the cold spot, a region of the CMB that is significantly cooler than its surroundings. Theories multiplied. Perhaps it was the result of a vast underdense region of space, a supervoid, through which light had traveled and lost energy. Or perhaps it hinted at something even more exotic, a bruise from a collision between our universe and another bubble in a vast multiverse. The deeper the measurements went, the more anomalies appeared. The CMB's smoothness was extreme, too extreme. In standard physics, different regions of the early universe should never have been in contact to share temperature information. Inflation theory explained this, but inflation itself was a hypothesis reaching into energies and conditions that no human-built experiment could replicate. Some physicists began to wonder, was inflation the only possible answer? Could the uniformity be the result of an entirely different mechanism, one tied to quantum gravity, or to a cyclic universe with no true beginning? There was also the problem of dark energy. The CMB's fine structure revealed that the universe's expansion was accelerating, driven by an unseen, repulsive force. Dark energy was not a minor footnote, it dominated the cosmos. And yet, no one could say what it was, why it existed, or if it might one day change, reversing the expansion into collapse. The CMB had begun as a confirmation. Now it was a warning. The more clearly we saw the early universe, the more we glimpsed the limits of our understanding. From these mysteries emerged a constellation of theories, each daring, each incomplete. Inflation remained the leading model. In its simplest form, it posited that a hypothetical field, the inflaton, drove the rapid expansion in the first trillionth of a second. This neatly explained the CMB's uniformity and the distribution of its fluctuations. But inflation came with unsettling implications, including the possibility of eternal inflation, in which countless universes bud off endlessly, each with its own laws of physics. Another idea, more radical still, proposed that our universe is not the only one, that the cold spot in the CMB is a scar from a cosmic collision, when another universe brushed against ours in the early moments of inflation. If true, the CMB would be more than a relic, it would be a message from beyond our cosmic horizon. Some physicists have explored alternatives to inflation. Bouncing cosmologies, where the Big Bang was preceded by a contracting universe, or holographic models, where space and time emerge from deeper, information-based structures. In these visions, the CMB might encode patterns that point to a pre-Big Bang era, the shadows of a time before time. Then there are speculations tied to quantum gravity. If spacetime itself has a smallest possible scale, the Planck length, then the CMB could carry imprints of that granularity, faint distortions from physics that operates beyond Einstein's equations. Each theory reaches toward the same truth: the CMB is not just ancient light. It is the most complete record we have of the moment reality itself began. The pursuit of the CMB has become a pursuit of the universe's deepest secrets. Planck's mission ended in 2013, but its maps are still being mined for information. On Earth, new arrays of radio telescopes, like the Atacama Cosmology Telescope in Chile and the South Pole Telescope in Antarctica, are pushing to measure the CMB's polarization patterns in exquisite detail. These patterns could reveal the faint signature of gravitational waves from inflation, a discovery that would be nothing less than a glimpse of spacetime's birth. Future missions, such as NASA's PICO proposal and the Simons Observatory, promise to go further still. They aim to detect the elusive B-mode polarization, a curling pattern in the CMB's light that inflation should have imprinted. If found, it would be the most direct evidence yet for that rapid early expansion. These tools are not just listening to the past, they're testing the boundaries of physics itself. By studying how the CMB interacts with galaxy clusters, astronomers can measure the universe's large-scale structure and track the growth of cosmic expansion. By refining the CMB's measurements, they can probe whether dark energy's influence is constant or evolving, a question with profound implications for the fate of the cosmos. The CMB is not beautiful in the way a galaxy is beautiful. It has no spiral arms, no glittering clusters of stars. It is a pale, mottled glow, quiet and impersonal. And yet, it may be the most profound image humanity has ever captured. It is the memory of the universe itself. A photograph not of a place, but of a moment, the first light after darkness. Every atom in your body, every star in the night sky, every galaxy that drifts through space, all of it traces its origin to the ripples in this light. When we look at the CMB, we see the universe before it knew itself. Before there was Earth or Sun, or even stars to light the void. It is the raw, unshaped potential from which all complexity would emerge, the moment before the first story was told. And in its quiet, it reminds us of the scale of the unknown. This light has crossed the whole of space to reach us, carrying with it the truth that our universe has a beginning. But it does not tell us why. It does not tell us what lies beyond our horizon, or what, if anything, preceded the moment it depicts. Perhaps that is its greatest gift, to remind us that the universe is not just a place to be measured, but a mystery to be lived. That in the glow of its first light, we can see both our smallest and our greatest selves reflected.